In this video, we're going to look a little bit at triple integrals and how they're evaluated. So the first thing is to look at the symbols that are involved. So we're looking at the triple integral, which makes sense. 1, 2, 3 integrals over S. And S here is some solid region in R3. So over a solid of a function f of x, y, z, dv. So not dA anymore, right? dA for double integrals, dv for volume, dv for triple integrals. So w, let's look a little bit more at the symbols. We're talking about w being some function f of x, y, and z. So obviously we don't need a w in the actual integral expression, but that is the way that we've written it in the past. And this function, we've also talked about things like this. This function can be interpreted or best imagined as either a density or a probability density at some point x, y, z in R3. So let's go and look at those interpretations separately. If f of x, y, z is a density function, so for example in grams per cubic centimeter, then the triple integral represents the total mass of this solid S. So the total mass, if we're talking about grams per cubic centimeter, the total mass of S would be in grams. If you're interpreting f of x, y, z as a probability density function, like we will further on in the course, then the triple integral over S represents P of S, where S is some event, it's some probability event that can be described with 3 components as a solid region in R3. So let's go ahead and look at how to evaluate these things. So the easiest case is where S is a box or a rectangular prism. And just like a rectangle, a box can be expressed as a cross product of intervals. Now we're not crossing anything like vectors, but we're using the same symbol. So because we're talking about a box, we need an x interval, a y interval, and a z interval. So this box, AB cross CD cross EF, that represents a box somewhat like what is drawn here, right? So we're considering this in the x direction. This would be from A to B in the x direction. In the y direction, it would be from C to D. And in the z direction, it would be from E to F, right? So there's a box as pictured here, AB cross CD cross EF. And the way that we would go about defining a triple integral over a box is by using a triple Riemann sum. So I'm not going to force you to evaluate a triple Riemann sum. We're just going to have this kind of idea in the back of our heads, but then we're not actually going to do any examples. We'll do simple integration like we've been doing for the double integrals. So the idea here is that you would split up your box in terms of number of subintervals. So along the x, there would be in the x direction, the way I've written it here, there would be m. Oh, this doesn't actually line up, but it doesn't really matter. M subintervals, intervals in the y direction. So in the y direction, I've written n subintervals, and by color, and in the z direction, I would have written p subintervals, right? So we're dividing this up into different subintervals, and if you take a little subinterval by a subinterval by a subinterval, then you end up by getting a little rectangular prism. A little, instead of a mini rectangle, you get a mini prism like this. So you've got your box all chopped up into little pieces. And the first thing that you do, if we go in sort of the order that it's written here, right, you look at the first Riemann sum, you're adding up the rectangular prisms in a row, right? So if you look at this, that sort of means adding up all across this row to figure out sort of the volume of a single row. And then what do? You add up, in number 2, you add up the rows. So then once you've got a single row, you add up all those rows, and then you get the volume kind of in a slab. And then once you've got a volume in one slab, you add up all the slabs back and forth until you have the volume of a box. And so just like you might expect, just like you did in Cal 1, Cal 2 actually, integral calculus. It's nice to know that I make the same mistakes in videos as I do in class, huh? That in Cal 2 you took the limit as the number of sum intervals went to infinity. So here, if we take the limit as m, n, and p go to infinity of that triple Riemann sum, right, then you end up by having not an approximation, but that is the definition. That's the definition of the triple integral over that box B is the limit of that Riemann sum, if that limit exists, right? And so going back and talking about our interpretation, if f is a density, right? If f is a density, then this triple integral, what you'd be calculating would be the mass of this box, right? The mass of this box up here. Now you can kind of imagine that, a box, it has mass. That triple integral would represent the mass of that box if f was a density function. If it was a probability density function, it would represent, this triple integral would represent the probability of B, where B is some event, which depending on the problem that you're given, you would determine that B being, or events in this range would constitute B, and it would be the probability of B. So if we're not going to actually compute Riemann sums, what are we going to do? We're going to do BNice theorem for triple integrals, and it's going to be exactly like you would expect after seeing BNice theorem for double integrals. And so that is, if f of x is continuous on the box B, where the box is AB cross CD cross RS this time, then the triple integral is, right, the triple integral over B of f of x, y, z dv is written as the integral from R to S, of the integral from C to D, of the integral from A to B, of f of x, y, z, dx, dy, dz, where the latter is an iterated integral. So the same thing as in double integrals, meaning an iterated integral, you start with the inner integral, right? Start with the inner integral. The inner integral is written with respect to x here. It's our x interval from A to B, which means you pretend y and z are constants and you integrate. Right? Then the next integral along is with respect to y from C to D. Then you do the next integral, and then obviously finally the outer integral. So you do these things in 3 steps, right? And so there's something a little more complicated about triple integrals. When you add another variable, there are 5 more or 6 total orders of integration. So I've written one of them here, right? I've written dx, dy, dz. Well, it could be dx, dz, dy, or dy, dx, dz, or and so on, right? There's 6 different possible orders of integration when we're talking about a box. So a box is analogous in this sense to a rectangle for double integrals. A box is analogous to a rectangle in that for continuous functions, the triple integral can be evaluated in any order, any of those 6 orders, and the answer will be the same. But that's for a box. That's for the simple case. So a little more care is going to have to be given when we are evaluating a triple integral over a solid S, where S is a more general solid, not necessarily a box. Changing the order of integration, right? It's still going to be possible, just like it was for double integrals, and just like for double integrals as well, it's going to require more care and more work. So let's go ahead and look at an example of triple integral over a box. And so this example is asking us to find the total mass of the box, so 0, 1 cross 0, 2 cross 0, 3, if the density, so we're being told to interpret this function f of x, y, z, given here as xy plus yz plus xz, as a density function. So that means that the total integral, the triple integral here, that is going to be the total mass of B. That mass of B will be that triple integral. And so because we're given a box, we can choose the order of integration. I have chosen to go in dx, dy, dz. So that means the intervals of the box must match. So the inner integral dx from 0 to 1, the middle integral y from 0 to 2, and the outer integral z from 0 to 3. So we go ahead and we integrate. We integrate with respect to x first. And so we're looking for antiderivative with respect to x. So we should see here, right, holding y constant, 1/2 x squared y. Y and z are constant, so x, y, z, again holding z constant. There's our antiderivative with respect to x, and we're running that from 0 to 1. So fundamental theorem, you're doing top minus bottom, and here is the result when you do that. Now we're proceeding with the next integral. The next integral is with respect to y. Now, so with respect to y, our boundaries are 0 and 2, and again we need to anti-differentiate. There are no more x's, so the only thing that we're holding constant are, well, numbers, obviously, and z. So we're going to anti-differentiate the y's. So antiderivative here, 1/4 y squared, antiderivative here, and antiderivative here, again holding z as constants. We're going to run this from 0 to 2, and this is our answer. And now we're in a situation that you could have been in, back last year in Cal 2, a simple integral, one variable, so you're looking for the antiderivative, or the simplest antiderivative here with respect to z. There it is. You're running this from 0 to 3, and if you do fundamental theorem part 2, right, top evaluation minus bottom evaluation, you should get this with the answer of 33/2 as the numerical value. Obviously, we're not given units here, but there would be some sort of units of mass, grams or kilograms or something like that, but we were told to interpret this function as density. So our final answer is going to be in terms of mass.